So this will be our last lecture today, well, for this course in general, and we'll talk about a probabilistic data structure. It's called skip list. And basically the idea is to have some sort of map set implementation, but basically we are going to offer log n performance, right? But it will be interestingly that it does not depend on our order of how we give data, basically. It will be randomized, basically. So you will basically, the idea is to offer randomized shortcuts to your data, where to go, basically. Really cool idea, basically. I would say actually it's more like a tree, but okay. So something like this, basically, right? It's like a linked list with shortcuts, basically, right? You have a linked list, and then you have multiple layers of shortcuts, like a top level shortcut, right? Basically, here in this example, maybe you can draw. I can draw here. Yeah, I can draw, or I can draw here, right? This one here, right? Oh no, this one here. Yeah. Draw. Yeah. So we have some data stored, right? But we also have some higher level items. So if you need to, you add on a random basis. That's a cool thing. You add them randomly. You add shortcuts. So for example, you add multiple levels. So here you have a top level shortcut, which says everything, where to find everything to the right of 21 and everything to the left of 21, right? And then you can immediately go down here next levels. So then, let's say you're looking for something like 15, right? You start this level, you know you have to go down levels. You see here, right? You go down, and then you check for 15, and it's here, basically, right? So it ends up being like a tree-like structure, right? So it's a way you can say, okay, it's a balanced tree, but randomized, in a way, right? So it has some nice, cool features, because it's relatively easy to implement. Also, you completely don't have to worry about your data order, because these shortcuts will be randomized. So as long as your random function is working, is good enough, you'll get this log n performance, which we are after, right? So again, if you look at our big cheat sheet, right? Skip lists are here, yeah. So log n, log n, log n, right? So the only downside, of course, is, what's the downside of the skip list? Well, you get this access, search, insertion, deletion, log n time.
It's complex.
You mean? Yeah, space, you saw this. Yeah, this orange part, yeah. So you need a little bit more memory, right? Also, some people, they say, okay, also it's they're not so popular these days because of something called cache locality. The arrays, modern machines, they hugely depend on this sort of like a very opportunistic looking forward when you're going through some array structure, right? There are all kinds of optimizations, right? All kinds of caching going on, right? And skip list is basically a bunch of linked lists, right? And the problem with linked lists in modern architecture is that you put them basically wherever, right? So, because again, so you can insert everything with log n time, delete in log n time, but again, if you are missing cache, right? If you're not hitting the cache, well, it will not be the best performance. But again, pretty cool structure. And also, if you need this log n performance, you can actually probably implement yourself. We'll see this, let's see a visualization, right? So we start, let me make this bigger, a little bit bigger. Yeah, bigger, okay. Right, so we're gonna be flipping coins basically, right? So, let's insert something. Let's insert 10, right? Let's insert 10. And obviously, we insert here, but also in this particular case, well, we've got amazingly crazy flips. This is kind of insane, actually, for first flip. We got 5 levels, right? Which actually could happen, right? So we added these 5 extra unneeded levels, actually. For some optimization, it would be maybe not needed, actually, right? So what I'll do is I'll kind of cheat. I'll get less lucky next time, actually, right? So I'll do it over, right? So this again is completely probabilistic. So insert 10, right? So I got 5 tails in a row. Right now I got only 1 head, or so I didn't get any, I completely failed, right? I didn't get lucky at all. Let's insert 15, or let's say 15, right? And we gain a level, right? So let's put some more data inside. Maybe we'll get to 20. So obviously, the lower level always contains all of the data. But the higher levels, by the simple probability, they'll get less and less data. They'll get the higher levels function as shortcuts. Because what's the problem with linked lists, right? You have linked list, you don't know where to go, basically, right? You have to go through each element. If you want to find some element, right? How do you find the middle element, right? You don't have a shortcut, right? Basically, then, you won't find it. So here, let's do 20. Again, we go here, right? We know we have to go down. We gain up? No. Okay. It's just probabilistic. So let's do 25. Again, the thing is, the order of insertion completely doesn't matter. All that matters is how lucky or unlucky we get that day, basically. Right. And maybe we'll get lucky. No, didn't get lucky. Let's insert 5. No, so far no luck. That's fine. Right. I got lucky on the first one, right? And now, of course, I'm not getting any hits. So right now, right? You see how I'm traveling? I skipped these two parts. You see? Now, okay. I guess I'll start doing something like 22 or something, right? So how will 22 be inserted? We start at the top level. We only have 2 levels at the moment, right? We'll check here, left or right. So we start here. So we're skipping this part here, right? So again, for a larger list, you'll get more and more efficient. Let's see here, you see? And we go here, on, 22, on, that's it. Okay, I'll keep waiting for my luck to change. Okay, let's do 18. No, let's do like 24. Again, we'll go here, obviously. I'm keep waiting for some flips. Yep, you see? And more higher level. Well, this extra level, I see again, I got like 5 flips in a row. This is a randomness, right? My random generator. So technically, some implementation of skip lists will see if you are adding too many levels, right? That you're doing it something it's like they're not really needed, right? They don't really add anything. But on average, you have thousands and thousands of millions of items by the law of large numbers. Probabilistically, your skip list will provide this log in performance. Right now, it's kind of bad. Because why? Because we'll start this top level, right? I don't really like this last one, but okay. Maybe I'll play around. Since I am like a demon, like a probabilistic demon, I know what the structure looks like, right? So I could play around. But the point is that usual user does not know which keys have these skips and which do. But I'll remove it. I'll remove 24, right? So obviously we'll start here, I'll go down. Right? It'll remove all of them. Right? Yeah, and that's it, right? So let's do it instead again. Basically I want like a couple levels. Right now all these useless levels are here basically, right? Right, these are basically Yeah, you see, I added maybe one more. Yeah, one more. That's it. Okay, so that's more like it, right? Again, I would like to just delete these 2 levels, basically, right? But okay. So now you see, in the real life implementation, a good implementation, these 2 will be, of course, will be skipped. But basically, you're looking for something. Let's look for something. Let's look for something like 22, right? If I look for 22, right? Lookup, right? How will look up? Well, in this case, we'll go here, right? These 2 levels are basically useless. We'll check here. It's less than 24. It go down. Less than 24, but more than 15. Let's see how it looks. Oh, actually here, less than 24. Okay, here, right, like this. So let me add 21. I'll add 21 with the lookup, basically. Yep, Okay, we gain level. Okay, now. So now again, you hopefully now you'll start seeing this actual the idea of the skip. Oh, what did I do? You see everything? You don't see anything? I don't see anything. HD. What? Okay, yeah. The cable. Okay, yeah. So now you start seeing, hopefully you start seeing this idea. If I look for like 22, I will be going to here, right? And I'll skip these values, and I'll skip this value, right? I'll be skipping a whole bunch of values to get 22. So if I look for 22, it will go through here. Right? So in a regular list, I will have to go 1, 2, 3, 4, 5, 6. Here, assuming, of course, I'll ignore this, we'll do 1, 2, 3, 4, 5. So I only gain something. Right? So how about 24? Look up. Well, 1, 2, and here. Right? And I go down, and of course, it is here. Right? Again, remember, these top levels, they're just shortcuts. They're just shortcuts to the actually what we are looking for, basically. Right? And they get smaller and smaller and smaller, and by probability, divide by half. Half less, half less, half less. Right? So what's happening at each time we add something, we do addition, we flip coin, right? And we decide on next level, do we want one level or do we want the next one? As long as we flip heads, we add a level, right? So probabilistically, if you have 1,000 items, on average you'll have like 9 or 10 levels, right? On top, there'll be 1 or 2 shortcuts which will have like, jump down, 9 levels deep, basically, or 10 levels deep, right? So the more data you insert, the better this gets, basically. So again, so there's some real big advantages and some of course disadvantages as well. Okay, so we have 1, 2, 3, 4 levels. So that means we could add like 16 items to get this 4 level, right? We need 1, 2, 3, 4 flips, right? 4 flips. Okay, let's add something more. Let's add like 28. Right? We jump here because it's over 24, right? So we again, and that's it. No, we still get lucky. Okay, 28. One more, 28, and that's it. All right. So now we have 2 shortcuts, 2 second level shortcuts. Well, 4, 2, and then expect gets another like 1 shortcut somewhere here. Well, I guess let's do 16 or something, or 18. See how lucky we get. That's it. Okay, I'll remove 18 because I want to actually show, because I'm playing with random numbers basically. I'm like replaying a game basically. I'm basically saying, okay, I don't like this save, right? I'll play this again. I'll load the game again and I'll try again, of course, right? But in real life, of course, since the user would not know which numbers hit the lottery, so to say, right? Let's do 18 again, right? I'll do it until I get 3 levels, basically, right? It's like getting a cheat code to play lottery, basically, or spin the wheel. I don't like my spin. I'll keep spinning again. So let's see, 1. No, okay, that's not good. I want more. I want 3 levels. Okay, remove 18. And again, I think it's right now when you have so few numbers, it doesn't look that great. I mean, but you see how to get to the end, right? If I want to get 30, I'll need to only do 1, 2, 3, 4, 5 jumps. I don't need to do all these 15 jumps. So towards the end, it gets really useful, actually. Of course, you have head and tail pointers as well, of course, right? That's also possible, but you don't, So insert 18. No, you're not getting my coin flips are not very good today. I'll mix faster, basically. Right? Yeah. Insert again 18. Okay, one more time. Oh. All right, let's do one more time. Okay, well, okay, let's leave it at that. Okay, I want to give one more level, but okay, I don't know if I'll get that lucky. So, if I look for something like 19, it will go through here and go through here, basically, right? Look up, right? You see? I'll make it slower now. So how about 20? It will go same thing. How about 21? Well, where will the path take us? It will go through here, here, and here. Is there a snipping tool? Yeah, there's snipping tool. Yeah, let's do this. All right. Let me do this in like, oh, you can paint stuff, right? Yeah, you can paint stuff right here. All right. Yeah. So, let's see if can I paint on this? Yeah, I can paint. Right. So, if I look up for something like, I don't know, so 25, right? It's less than positive infinity, so you go through here, right? Right? And you know 18, it's 35. Let's say looking for 35, well, or 25, right? Look up, right? And of course it is more than, right? 25 is more than 18, right? So we go here, right? And well, it's also more than 25 is more than 24, right? So we go here, right? And now we go back, right? Less than 28, right? Right, 25 less than 28, right? So we go down here, right? And then of course at the base level we go until we either overshoot it, then it doesn't exist, right? So again, I'm going to discount this highest level, right? But so you have, let's see, we only have 3 levels. So 1, 2, 3, right? Basically, so 1 jump, 2 jumps, 3, 4, 5. So 5, right? So 5 jumps, right? How about, let's do another color. Where's color? Black. Oh, black. Let's do red pen, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. So half, almost half the size, right? These jump lists, again, so skip lists, right? These shortcuts, again, on average, will give you this log n performance, basically, right? So here you only do 5 jumps, basically, right? So on average, you have how many items you have? Well, see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So log 2n, well, you would want, of course, ideally we have only 3 jumps, right? But again, the thing is the growth, right? Remember, there's some constant factor, right? Well, we set up the growth factor will be this log n, basically, right? So basically it's going to be some constant, right? There's some extra jumps, you know, sort of like initialization, basically, right? Always happening, but the rest will be log n again. So does this idea make sense at all, or kind of?
Yes.
Yeah. So it looks fine, right? So the question is now, can we implement this in C++, right? But it's basically a whole bunch of linked lists, basically, right? So let's see. We have some time. Maybe we have 15 minutes. Okay. We have like 20 minutes. We can do this, I think, right? So let me save this. Can I save this as a PNG? Yeah. Skip list. Right. Look up. Okay. Now, so let's see what the theory says, right? Visual, we saw this, right? And also, let's go down, right? I talked about this, right? So a couple levels. So this would be a perfect, well, perfect skip list would be like this. Let's see, we'll show you. So, yeah, if you get the perfect, right? Perfect skip list would be, of course, you have one highest level, only one, like right in the middle, right? And then you have 2, right, sort of like in between, right? So sort of like something we do in a binary search, right? But we don't really get the perfect skip list, right? Because you have to keep rearranging. You don't want to rearrange. So this randomized skip list avoids all of this, right? Yeah. So this basically gives you expectation, right? This shows why it works, right? You have an expected value, right? So you have a game. Somebody gives you a coin, right? You get $1, right? If it comes heads, right? But if you get tails, you stop. So how much money will you be getting, right? Right, that's on average, right? So you get 50% chance of getting $1, right? 50% chance of getting nothing, right? The expected value, right? So $2, $4, right? So, right? So on average, right? Yeah. So on average, there will be n divided by half nodes promoted to the next level, right? Each level, as levels grow, you get less and less nodes getting promotion, basically, right? It gets less and less likely you will win this, you know, this whole head flipping game. So that's the basic idea, right? So what other disadvantage of this skip list, of course, is that you need a randomized function, right, to do this, right? So if you're inserting, so you need a really cheap random function. That's also a minus, right? If you are actually not doing too much of access, meaning not doing, once you insert it, right, for access, it doesn't matter. You have it already probabilistically. But while you're building it, a good, quick, random function will also be crucial. I mean, what good is skip list if it takes, there's like this huge, I don't know, really bad random function which takes like it's like linear time or something, which shouldn't happen, right? So that's a cool thing. So yeah, so this would be the worst case skip list, yeah. So this is like, would be basically like a linked list, basically, right? But the idea is this, it's basically extremely unlikely to get something like this, you know. Top level, then go down, like this is not going to happen. On average, basically, you know, you're not going to get this type of bad performance. You have to get extremely unlucky. When I say extremely unlucky, you know, you have 1,000 elements, 2 to the thousands, right? That's already gives you, you know, on average, you will get a log n performance. So it's amortized performance. Right. So analysis again, right. So, right. So we can either we look for something like 28, here same thing, right? We check, right, it's over 15. Next is over 21, we keep going down, right? It's over, you know, it's the event we find here, or we look at something like 30, right? We'll go 1, 2, 3, 4, 5, and 6 here, right? All right. Again, so analysis, this is from USC Viterbi School, will show you this is actually log n, right? So this looks like, actually this looks like C++, actually, yeah, you can use this actually, but let me see if I can do it actually by myself. Right. GitHub. Right. On, let's see our data structures. I think we can do it. It's certainly easier to follow, the logic is easier to follow than, say, playlists, right? Or any type of tree structures, right? Much easier. Skip list. Well, of course, you'll need a linked list for this, right? We have, no, okay, let's do a linked list. Could we use a, we could of course kind of cheat, we have a double linked list already, right? Yeah, let's do, so I don't want to reinvent a linked list, right? Because that's, you know, I mean I could, but it's not the end of the world. I think we have double linked list built in into standard library, right? So let's use that. So skip list, right? Let's build a skip list. For integers, right, we will use existing doubly linked list from library. List. Yeah, exactly. Include IOStream, include vector. I guess we could cheat on using vector. We can use vector because it's dynamic, right? We'll use vector. But I would like to, let's see, I thought there was doubly linked list built in. Let's see, doubly linked list in C++, std, I think it's that library. I think there was one C++ reference. I think there was one, if I am, unless yeah, it's there, right? It's not guaranteed to be doubly linked list, but it exists, right? List, let's use a list instead, right? We will be using a list, right? Not vector, right? I mean, we can use vector, let's not use vector. Let's use the list. Include the list, right? Can I do this? I thought this should work, right? It says no, it's legal, right? We have front, back, right? Insert, pop back, right? Doubly linked list. Yeah. Do we need algorithms? Why do they have algorithms? For what? For find. Yeah, there's an algorithm for find. Maybe we'll need algorithms as well. Maybe. I'll include algorithms. Maybe. I don't know. Maybe we don't need it. Let's see. Using standard. Alright. So node, right? So basically, we don't need nodes already, basically a list number, right? It's basically generic, right? Template based, of course, right? Any, So yeah, that works. So I think we only have, since we only have, so yeah, class skip list again. We'll see how it works. Public, right? So no private, right? New node. We don't have node yet, by the way, right? Head tail, head right, skip list, insert. I think it's gonna skip. It's gonna do it everything by hand. We need a node then, right? I guess we'll do a node then, right? In minute max, yeah, okay. We need node first. Let's make a node first. Class node. Wow. All right. Class node, right? Up, down, right? Okay. All right, that works. Now new node. Constructor. Now looks okay. I need include the limits, right? C limits include C limits. Yeah. Okay. Now head tail. Public. This is public. This, right? This head. I guess I need this, right? Yeah. On this head next. Yeah, but they use this trick, by the way. This is also a common trick. This head next, right? That works. Let's see. Why doesn't it work yet? It's not picking up this. On this level. Yeah, I guess we need special structure for this. Level up, down, this value, right? So level, yeah, level is included, but we don't have the private. Basically, we need private, right? Private, head, tail, and level, right? That's more like it. Okay. Now it's looking better. All right. So we'll I guess we don't need random. We don't need the algorithm and random. I guess I'll see if we can skip it all day, right? Yeah. Insert. So where is our random insertion base? So insert. We go through levels. Yeah, we have a random function. Okay, so this is the part here, right? Level. If we need insertion, we might randomly we advance level. If the current level is more than level, right? We increase level, create a new node, right? And create new pointers, basically. Yeah. So yeah, I guess we can't use yeah. So we have basically so the cost is some extra pointers, right? We have down previously, right? And also while we go and we add the extra pointers. All right. Now, all right. So new node. You could probably do it recursively, right? I guess. I think that's it. One more. Or we're forgetting something. Okay, this is. Oh God, there's so much stuff. Okay. Getting kind of messy. And we're almost finished. Insertion is pretty painful. Let's see. Yeah, okay. And what else? And this was for what level? Let's collapse these levels, right? Because it's getting kind of crazy. Okay. That's the big while loop. And this was, of course, let's collapse some of these levels. Right. Okay, looks okay. So that's the insert. So now we need the deletion, remove or delete, right? So removal is basically you start. Well, if you think about it, you remove it from all the levels. It's just a bunch of linked lists, right? For each level, it's just a whole bunch of pointer reassignment, basically, right? Current is head, right? Next is null pointer, right? Right. So while you have a pointer, right? Well, it's not null pointer, right? You keep adding it. So delete next. So this, of course, is very. You have to be very careful. Now find. Right. Find bool search. Does it exist or not? Okay. I think that's it. Print. Void print. I guess you can print, right? Current head, right? Well, next, right? Okay, and I think that's it. I hope nothing else. Oh yeah, we need the constructor. Yeah, we need the constructor. Basically, delete everything, right? All levels, right? Now I think we are good. Yeah, we are good. Hopefully. Yeah, and now we can see if we can do this. Let's see if this actually works, right? Yeah. So int main, I will provide. We will provide some numbers in command line arguments. Int main, right? Our count. Yeah. New skip list, right? Insert. And assuming, of course, we assume we will provide integers, right? All right, and then let's not rush ourselves, right? Do you think this will work on the first try? I'm doubtful again because there's a lot of pointer manipulation, so it's possible we go really badly wrong, right? So let's compile it. Let's compile this whole thing. G++, val, skip list, skip. Well, it compiled. That doesn't mean anything, of course, right? Skip. I'll do 1, 2, 3, 4, 5, right? Wow, it worked, but there's also infinity, right? So it works, but we also, of course, we printed also the infinity as well, right? We have the infinity marker, right? So it's one of those little tricks if you're actually implementing this, if you had to actually do it yourself, right? It's very typical. You need some sort of marker, right? In this case, it's maximum value for max integer, right? So the last item. So in skip list, you have to negative infinity and positive infinity, right? I mean, you can use some if statements to sort of always check for it, but it's basically the markers or sentinel values work best. All right. So let's see what happens. Skip. What did we do here? Okay. Inserted. We printed. Okay. So next time I run it, let's do it again. Yeah, let's do it again. Well, looks like it's completely deterministic. Let me do some random seed, all right? Let's do some random seed. Let's do some seed. Let's set up random seed. Yeah, time 0. I forget the time. Yeah, this is typical, right? Obviously, this should make some things a little more interesting, right? So our levels, right? So what happened is, of course, we get 3 levels basically here. It looks like. I don't know why this one showed only 1, right? Okay, let's see. Let's do it one more time. All right. Okay, 1, 1, 1, true. Okay. Different. Right. What's interesting here is the printing, right? So it prints each level, right? 3, 1, right, for each level. There's skip list. I think there's some. It's not. It looks okay, the part here, but I wonder what's happening here, right? You're inserting 1, 2, 3, 4, 5. So if I insert, let's do this. So 10, 20, 30, 40, right? Right. 10, 20, 30. So what's the question is why is there 40 here? Why is there 30 here, right? So something is not quite right. Let's see, we have some ways of actually working on this. Now search is okay, print. Okay, node current. So it looks for the current head. So head is from the, what is the head value, right? Head is top level, right? To int min, right? How will head be adjusted, right? When you insert something, right? It's a question of where we start. Could we always, so let's see how do we save this, right? So skip list have head and tail basically, right? So we would like to see the head should be basically, should be this, right? This would be the head, right? Whereas, so this would be the head. Right, and tail, basically, right? Tail. Okay. Alright. Of course, it goes down, right? For each level, right? So head and tail in each level also. Head, right? Head, and so the tail, 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 and so tail, tail. Of course, in this case, talking about heads and tails, since we are flipping coins, of course, maybe using similar terms, right? We also use heads and tails when we're flipping coins, so 0.5, right? So, so let's see what's happening. Why are we the printing? We have head to head. This part here, it seems like when we are going through the print. Let's find 20. Let's check 20. Let's check for 20. Let's see if 20 is found. Bless you. Thank you. Right. Let's see if this works now. Oh no, I don't skip. I want to compile. Oh no. Yeah, it is true. Let's do Shift Alt arrow down. Let's say 50. Let's see if it works, right? So search works. Well, we'll see if it works. Yeah, but work. Okay, so if that part works, the printing is kind of wonky a little bit at the moment, right? So insertion works. Let's insert 50. Right, let's insert 50. Let's insert 50. Check again. On print. Yeah, remove 20. All right, let's see if this happens. And then print. No, finally print. Let's see if all the pointers work. Print the list. All right, let's see if this happens. Compiling, that's fine, and skip. No core dumps. Everything looks good. Actually, everything looks good, right? All the operations work perfectly. It's just the printing is kind of weird. You're printing all the values, right? What I don't get is why is this second level, we print the first, like the highest level, then we print this level, which seems like and then we print the bottom level, right? But why it's sometimes, right? It's probabilistic, right? Right? Now here, look at what happened here. Is this maybe not clear, or is there something more going on? Yeah, so sometimes it works completely perfectly, and sometimes you get doubles, right? So when I print the level, right? Let's print the level, right? And when we print, right, do the nodes, what has level? Level is skip list level, right? So the node itself does not have a level, right? Unfortunately. We can't print the level, but this level, printing, we have? We printing? Do we? Okay, go down. Unfortunately, we don't show the level then, right? Because the level is not added to the node, right? We could add it to the node level, right? For debugging purposes, right? It's of course kind of wasteful, but I'll add for debugging purpose, I'll add the level to the node. Let's do that. Node and level. All right. Yeah. So this will be maybe useful to value. We will need, of course, to level, right? Level. Yeah. Of course, up, down, right. Okay. Now we can print the levels. So whenever I make a new node, right? Level, right? So I'll need this first, right? So I'll add this first, right? In the construction, right? We will add a level here, right? This level. This should be legal. I hope. Yeah. Okay. Now, whenever I make new nodes, again, I need to make a new level. And the thing is, insertion, right? Let's see about this level. And where's my level? Oh yeah, or level basically, right? Okay. So, okay, second. Another call. Ja, lūdzu, fokus. Jā, klausās, jā. Jā, lieliski. Jā. Jā, jā, noteikti. Man vispār būs vēl papieru domzīmē. Jā. Jā. Labi, tad liekam visu kopā. Jā. Jā. Lieliski. Labi. Paldies. Alright, okay. Now, I'm going to reverse with the levels, and now we have to check when we're inserting, right, the level when we're creating a new node. That's not new node, right? Only where are we creating new nodes, right? Not here. Here now. Right, increase level, current level. That might be important. Here, right, okay. So level plus plus, and of course we add new level, right? Level, of course, or this level, same thing, right? Level, right? Okay. Will this work, or you may be missing something? Here as well. Previous level. Now, good question. Is this actually previous level or actually level? Right. That's a good question, actually. Previous level, right? Level. We'll see if this makes any sense, right? I don't know what to put in here actually, right? So I guess it's putting it to maximum level. Alright. And this one here, previous level, new up. It's looking slightly suspicious actually. But this is what removal is okay, search is okay. We don't do any work there. And when we print level on, we want level. Yeah. Okay. Let's compile it and see if we get anything actually out of this. Maybe this looks like complete hot garbage. And so no, compiles. That's good. Right. And we want level. Level. Yeah, it's no, it prints it. Oh, it prints all. I see the order. Okay, it makes sense now. Okay. Right. Okay. Yeah. So 10 is level 1, 30 level 1, 40 level 1, 50 level 1. Right. That's also level 1. So in this case we have nothing here. Let's do it one more time. All right. Okay. So we have level 2. Right. Yeah. It prints basically, it has extra traversal. So 30, right? All right, let's do one more time. Yeah, do we have any more levels? Only 2 levels? We do have third level actually, right? We do have third level here, right? Yeah. So there is a third level actually, right? But looks like it's not completely correct actually. Why? This 20, right? This should be actually level 2 actually, right? So there is a shortcut, right? And actually all the question is, we printed it actually. Well, I didn't. All right, I didn't delete it, right? I deleted 20, right? Of course, this remains, right? So let's do it one more time. We'll do it like 50, 5, 60. Let's do that. Okay. Yeah, we got third level now. We got to the third level. That works, right? So it is possible. No, so no levels are adding. If I add, as I add more items, like let's add something like, 1, 2, 3, 4, 5, 6, 7. So basically more coin flips, right? More coin flips. All right. Plenty of coin flips, right? All right. So should we get three, maybe 4 levels now? Hopefully, right? Yeah. So now it works, but yeah, 3 levels. Yeah, we got 4 levels now, actually, possibly, right? But again, as I mentioned, it's not completely correct. This should be added actually. When we insert these extra levels, we actually need to the insertion names. The levels are this needs to be fixed basically. I'll add it again. The higher level nodes are not getting correct level numbers. Okay, that's something to fix me. But again, I'm probably pretty tired, so enough for today. So, what did we learn today? About idea that we can create a structure probabilistically, right? So again, by flipping coins, you can create something which is actually useful, right? Again, there's a whole field of algorithm theory where you study these probabilistic structures, different ways of basically using randomness to actually ensure some efficient access data or perform some specific operations. Alright, so I will see you guys on Tuesday morning for the algorithms presentations. Super.